Welcome everyone, good evening, thanks for attending this talk. So, I am delroth, this is Shofal2. We have another member in our reverse engineering team, which is called Booto, but he couldn't make it for 30C3 this year. So, we're basically console hackers and emulator developers, so we work on the Wii, on the GameCube, and we're like developers of the Dolphin emulator, which is a GameCube and Wii emulator. And we help on this Wii U reverse engineering project by friends from Fair Overflow, which you might have seen on day one. They basically cracked open the Wii U and made it possible to do this work. So thanks a lot to them. So for those who don't know what the Wii U Gamepad is, so this is the Wii U Gamepad. This is what you actually connect to the console to play games. It's codenamed DRC. So we're probably going to use DRC a lot in this presentation just because it's a lot shorter to write and stuff like that. So just know that DRC is basically the gamepad. But it's like, as you can see, it's not like your standard GameCube control or thing with just like 2 joysticks and a few buttons. It has actually lots of features. So the main feature is it's a wireless device. Like you don't have to plug it to your Wii U or anything. It's kind of standard nowadays, but still. It has an 854 by 480 touchscreen, which is resistive, so it's not like capacitive touchscreen, it's just resistive stuff. It has audio output and also a microphone. And to go with microphone, it has a VGA camera, which outputs like a 640 by 480 resolution. It also has like the standard gamepad stuff, so analog sticks, 19 digital buttons, motion stuff like accelerometer, gyroscope, compass, and a few other wireless stuff which are interesting, like NFC and ARIA, which is used actually to use a gamepad as a TV remote, like it can communicate with your TV over infrared. But one big problem with it is that it's actually only usable with the Nintendo Wii U. So unlike Microsoft and Sony, like for the Xbox One and the PS4, they actually like told people, we're going to release driver at some point, and you can use it with your PC, etc. Nintendo like never said anything like that. They just don't plan it. They just don't plan for it to be open, just like the Wiimote before and all of their other devices. So it's kind of sad because it's a really fun device. Like you could use it to actually do a lot of stuff, like control robots or just play your games like without being in front of your screen. So yeah, let's fix that. This is like the whole point of this talk. So let's open the box. This is the motherboard of the Wii U Gamepad. As you can see, it's actually a quite complex device. The main chip on this is in the middle, like the big one. It's actually like an STM8 CPU from ST Microelectronics. It's called the UIC, like it's written UIC on it. This is the first of actually 3 CPUs that are on this gamepad. On the left, you can actually see like there is a big empty space. See where you connect the Wi-Fi chipset. It's like, it can actually be detached. It's a Broadcom Wi-Fi chipset, kind of standard. And on the bottom right, you also have an empty space, which is for the NFC antenna and NFC controller. This is the other side of the motherboard with more interesting stuff. The chip, like at the rightmost, is basically the flash that contains, well, basically all the code and firmware and stuff for the gamepad. And the CPU just at the left of the flash is called, like, it's written on it DRC-WP, and the only other marking on it is like Japan. You have like no other indication of what this chip is. And we'll see later on that it's actually the main CPU that controls most of the gamepad. This is on the other side of the system, so on the Wii U motherboard, not in the gamepad. So on the left, you can see the main bundle with like the CPU and the GPU of the Wii U. And at the top right, you have the DRH, which is basically just the same as the DRC, the microcontroller on the gamepad, but it handles communication between the Wii U and the gamepad. So how does it actually communicate? If you look at the back of the Wi-Fi chipset, it actually indicates 5 GHz for use indoors only. And it's actually a Wi-Fi chipset that's very common. So you can just like look online and start sniffing Wi-Fi on the 5 GHz frequency band. But obviously, it's encrypted. It's not that easy. So just as a side note, This is actually a big problem with this project. Finding a properly working Wi-Fi device is that can actually do access point mode at 5 GHz channels is really hard. Especially on Windows, it's basically mostly impossible. On OS X, I think some people actually manage to get access point working, but not with all the features we need for this project. On Linux, there are actually only a few drivers that are able to do that. So for example, if you take Intel wireless devices, there is no AP mode support on most cards that support 5 GHz. On Afros devices, you actually can find a lot of these cards, but they have minor issues which I'm going to talk about. Car 9170 is basically the same as ATH9K, but for USB. For some reason, it's very hard to find devices that use this chipset. So there are the same minor issues at ATH9K because it's basically the same chipset inside, but they also have the same minor issues. And then this one is interesting. The Warlink RT2800 USB is actually a nice USB chip, which is not too hard to find, has no major issues, but it only started working with Linux 3.11, which is fairly recent, so it wasn't actually working when it started this project. And yeah, we might actually be able to work as well on Broadcom chips, but we haven't tested that yet. So let's work on decrypting the communications between the Wii U and the Gamepad. We basically need two things. First of all, how is it actually encrypted? So maybe WPA or something like that. And what's the key used for encryption? So it was actually very easy to find strong signs of the encryption scheme. If you just look at the 802.11 header, the packets that you sniff, it's just like WPA2 packets. It has this protected bit that's set in the header to say that the header is basically integrity checked by the encryption scheme. And you have 8 bytes after the 802.11 headers that are incremented for every packet, and this matches what WPA2 does with the CCMP IV. So it was, just looking at it, was really lucky that it was using WPA2. So we just need the key now, and it was actually harder than expected. Actually, no, it was, well, they made it easy for us compared to just having to hack stuff. They actually have a nice feature on the Wii U. When you want to connect a gamepad to a Wii U for the first time, you have to pair it with a console. And what this pairing system does is you have the Wii U displays 4 symbols on the screen, and you have to type the same 4 symbols on your gamepad, and then the gamepad can connect to the Wii U. And looking at dumps, it's actually using WPS. So WPS is Wi-Fi standard that's used for auto-configuration of Wi-Fi devices. And basically what it does is use WPS with access points you don't know about, and they give you all the information there, including SSID, encryption method, encryption key, and everything like that. So WPS is secured, by the need to press a button on the access point or to enter the pin that's shown on the access point, so to prove that you have physical access to the access point that provides you the Wi-Fi network. And the specification is kind of interesting because it really doesn't make a lot of sense. It's extremely complicated for something that should be simple. It's just check that the guy presses on the button and sends them the data. So this is actually how WPS works. There are actually 8 steps to the protocol. As you can see, it uses encryption, Diffie-Hellman, HMAC with 2 separate hashing algorithms, custom key derivation functions, and a few other stuff like that. I'm not going to go over it. The interesting thing to see in there is that basically you only get the config data at the end, and that each step basically checks if they do an HMAC over this message and the previous message, so that you can check that the messages weren't tampered with. So obviously we tried to pair our PC with a Wii U just using WPA supplicant, which is a standard Linux program to do WPS, and it failed. So as you can see on this Wireshark dump, it fails at M2. M2 is the second stage of this WPS stuff. And what's interesting is that it's not actually the Wii U sending us an error message, it's actually us not recognizing what the Wii U sent us. So WPS applicant sends an error message saying, sorry, I can't authenticate to you. So we looked at it a bit more, like why is it actually failing? It turns out that this part, like the HMAC of the previous message plus this message, is actually not correct. Like, which would mean, the interesting thing in this is that there is no user data. We don't depend on any user data for this HMAC. So that means that basically the crypto was changed. So they took WPS, but it's not exactly WPS. They changed stuff which makes it fail at M2. So always like, what's actually failing is that the hotkey that's used for the HMAC is not the same. And the hotkey is derived from something called the KDK, and you can see it uses like a string constant, Wi-Fi, easy and secure key derivation. So it takes the hotkey from this key derivation function, and it uses it to, well, this is what is used for HMAC. So KDK is derived from N1 and N2, which are basically random values, and the MAC address. So yeah, nothing depends on user data, nothing depends on symbols that we should have to enter. So everything should just work if there was nothing doing a man in the middle, but it doesn't. So that's when we actually started to do some real stuff. So I let Shuffle explain how we actually worked on dumping the firmware.
All right, so when we got the gamepad, one of the first things we did was just inspect the board and dump all the flashes that we saw. And it turns out that everything is unencrypted and plain text. And the flashes were really easy to connect to. And we did have to make some changes to flash ROM, but it wasn't very difficult. And as soon as we did this, we could start looking through the firmware that was contained on the chip and look for the interesting Wi-Fi stuff. And I always have a picture of our respective setups. And so before we could actually look for Wi-Fi code, we had to determine the file system that Nintendo was using on the flash chip. And it's just some custom thing that they threw together with a really simple header. And it contains 2 different banks, so they support safe flashing, so they can flash a new version and switch to it atomically. And within the blob, or within a version of the firmware, there's multiple blobs, which are LVC, Wi-Fi, and UMI, among some others, which are like picture resources. But these are the main interesting code ones. After inspecting these blobs, we found out that the LVC is for the main DRC chip, which is ARM 926 EJS. And the Wi-Fi blob is for the Broadcom dongle, which is ARM Cortex-M3 code. And the UMI blob was for the STM8 UIC controller. So we knew from before, we knew that the string was involved in computing the KDK, and simple grep returns that it's only existing in the LVC blob. So after looking at comparable implementations in host AP, we can see that we should see some kind of HMAC SHA-256 being returned and entered into the KDF function as an argument. So through the magical power of hex arrays, we find this in the LVC code. They're just doing standard HMAC SHA-256, and after it returns, they're doing some post-processing to do rotate left 3 on the buffer. And that's the only change that they've made to the algorithm. So this is the crypto.
What's next?
Yeah. So let's go back to WPS. So now we can actually go further than just the second stage. So we need the WPS pin to be able to authenticate to it. But it's 8 digits, and the Wii U only shows us 4 symbols. An interesting fact in the WPS specification is that they designed it in such a way that there are 2 stages validating the first 4 digits of the pin, and 2 stages validating the last 4 digits of the pin. Which doesn't make any sense, because basically instead of having to test 100 million pins, like if you had 8 digits and you wanted to try each of them, you only have to try 20,000 pins to actually go through the whole space and brute force a pin. And another interesting fact is that normally most people implement the WPS pin by showing the pin on the device and asking people to enter the pin on the access point. And what Nintendo did was like the opposite. They show the pin on the access point, the console, and they ask the device to, they ask the user to enter the pin on the device, which is a gamepad. And that means that, unlike the opposite way, which is the usual usage of the WPS pin, you can actually brute force the hash offline without having to ask the console every time, hey, is this a correct pin or not? So it actually only takes like a few milliseconds to just find out the pin. And so yeah, this is just how it works. Basically, you have these 4 symbols. You just replace them with the corresponding digit. Yeah, and advanced crypto stuff, I know. And the second half is basically 5, 6, 7, 8, which is interesting because it actually violates the WPS standard, which says that the last digit should be a checksum. So, yeah. It's actually another interesting fact because it's because you know the last digit is a checksum. If you've already brute forced the first half, you only have to brute force 3 digits of the second half. So it's not even 20,000 combinations to test. It's only like 11,000. Yeah, WPS. I don't know what they were trying to do with this in the WPS standard, but it doesn't make any sense. And other people have actually exploited that. So you can look at River WPS, which is a tool to brute force WPS pin on standard devices. It basically just does that. So yeah, after that, this is the last 2 steps of the WPS uncheck. So the Wii just gives us the information. So hey, this is the SSID, and this is the 32 random bytes key that you need to use to connect to the network. Great. But obviously that would be too easy. Because we try to use the key to connect to the network like usual, and the WPA uncheck fails at stage 3 or 4, which usually indicates that either the key is wrong or that the algorithm was modified. And I mean, since the Wii U just gave us the key, and that we found actually nothing, the firmware code that modifies this key before passing to the Broadcom chipset, we thought, well, unlikely that it's actually the key that is wrong. Like, it's actually using the key normally in the code. So let's just look at the algorithm again. So to decrypt packets and to do the handshake, the WPA uses a key that is called the PTK, the pairwise transient key. It's like specific for every device connected to the access point because it uses MAC addresses and stuff to generate it. And so it basically runs a custom SHA-1 function on the PMK. So the PMK is just the passphrase that the Wii U gave us, with like a string, so yeah, yet another useful string to grep for, and it generates a PTK. And for some reason in our case, like the PTK was just like not the same, or it couldn't decrypt what the Wii U sent us. So let's look at the Wi-Fi firmware this time, because this is the only place the string constant is present, like the pairwise key expansion string constant. So this is Cortex M3 code, and what's interesting is that we started looking at all the Broadcom firmwares to see how they work, and we looked for the same string, it wasn't present. And it turns out that looking at what other people did with Broadcom firmwares, we're able to see that usually Broadcom chipsets implement some features in hardware, and there is actually like a function table at the beginning of the firmware that allows you to override functions, like hardware functions by software functions. And another interesting thing is that if you look in TDWRT SVN repositories, they have this copyright Broadcom confidential code checked in. So this is actually very useful because there is just the firmware code available. So this is from this DDWRT SVN. KDF can actually point to either the hardware implementation or in our case the software implementation. And so what it does is it takes the PMK, which is a passphrase, and it puts it in PRF buff, and then PRF buff is copied to PTK. Very easy. So this is how it's done on the Wii U. at least on the gamepad. So, can you actually recognize what this does? Yeah. It was fun to find, as you can expect, especially since we're skipping all the reversing, the reverse engineering part, but it took us a day or so to actually figure this out after finding out the WPS stuff, and we found out another word free, really, Nintendo, please. And yeah, this is actually the only steps that are required to be able to connect a Wii U, to connect a PC to a Wii U, or to connect a gamepad to a PC. And also, since to be able to sniff WPA2 data, you only need the handshake and the passphrase. If you can do that, you can sniff without any man-in-the-middle interception stuff. So this means we can actually just connect our normal gamepad to Wii U and intercept everything that's going on and inspect it and see what's actually going through the Wi-Fi network. So this is a very quick analysis with Wireshark of stuff that's passing through from the gamepad to the console and from the console to the gamepad. So as you can see, they're actually using IP on this Wi-Fi network, which is interesting. It's only 2 devices. So they use 192.168.110 for the Wii U and 111 for the gamepad. And potentially, you haven't seen that in use yet, but 0.12 for the second gamepad, which it's interesting because they say it supports it, but we haven't actually found anything that supports it yet. So there is only one thing going from the gamepad to the console. It's this port 50122. It's sending one packet. It's sending 180 packets every second with stuff that was actually very easy to recognize as input data because if you press a button, it just changes. More interesting stuff like port 520 and 521, which are probably video and audio data, because, well, there's just a lot of data and it's going only one way. And the last protocol is actually, it actually has the same number of packets on both sides, so probably just reply response. It's easy to confirm that by just looking at the exchanges. So another surprise for us is that there were a lot of articles on the internet saying, oh, the Wii U is using Miracast to connect to the gamepad and stuff like that. So we're really assuming, oh, we just find something standard and be able to just implement Miracast in Linux. It turns out, well, I don't know what journalists got this idea, but this is actually completely wrong. There is no Miracast used anywhere in the Wii U. It's actually only using completely custom protocols over the Wi-Fi layer. So everything is based on UDP, but you have one protocol for video, one for audio, one for input data, and a 4th protocol, which is just a simple RPC thing from the Wii U to the gamepad for stuff like, oh, turn off the screen, or adjust the screen backlight, or send this NFC command or something like that. It's a very easy protocol. Audio and input are also very simple. It took us a few weeks to get very good implementations. Last year at the Congress, we were actually figuring out input data, and most of it was straightforward. Video actually was way more complicated, and that's why we didn't actually present last year, but only this year. It took us actually far too long to get video working. It's actually a very recent development. 2 months ago, video was still not working for us for some reason. We were able to decode stuff, but not re-encode stuff. So yeah. This is what happened basically this year. We just stared at IDA for a few months and magic happened. So the gamepad is actually very complex. You could see on the PCB that you actually have 3 CPUs. There's actually a lot more chips on it, and you have this main CPU, which is a DRC WP, which is an ARM9. It's a custom system on chip. There is no documentation about it. We're assuming that it's made by Megachips Corporation, which are working with Nintendo for some stuff. It has 4 megabytes of RAM on chip, and it has a custom H264 decoder for video. It communicates via SDIO with a Wi-Fi chipset, which is very standard for embedded devices. And it has an I2C bus for a few stuff like LCD controller, audio control, and NFC. It has a UART for the RF stuff, and most importantly, it has a SPI bus to communicate with the flash, which contains the firmware code, and the UIC, which is another CPU, which is a STM8, like a really embedded CPU, which is not really powerful. And the CPU handles basically correcting all the inputs in the gamepad and passing a big blob of data to the DRC, which contains like the value of all the inputs. So the UIC itself has another SPI bus and another I2C bus, which are connected to all the input devices on the console, including, by the way, the extension port, which is like at the bottom of the gamepad, which currently has no use except provide a way for Nintendo to like boot the gamepad in debug mode. Well, not in debug mode, but in like repair mode for factory returns, we guess. On the Wii U, we have another system on chip, which is the DRH, which is extremely similar to the DRC. So it's another custom system chip with about the same amount of RAM. And it handles communication between the DRC and the Wii U. And this DRH communicates with the rest of the console over USB, like it's exposed as a USB device to the Wii U operating system. And over that, it passes webcam, microphone, input, and commands. And it also gets video and audio data directly from the Wii U GPU. It's configured like as an output head, like just like the HDMI chip, and it directly gets video data from there. So let's look at the firmware of the gamepad. So it mostly contains this LVC blob, which is the firmware for the ARM9 CPU. It's based on eForce Micro C3, which is a Japanese real-time operating system, which is fun because that means there is no documentation in English, obviously. But it's implementing like the Micro i2 4.0 specification, which is like an API for real-time operating system, which is implemented by like a few real-time operating systems, as far as I know. Like RTEMS is like an open source, RTOS implementing it. And this specification actually like is very well documented. So it runs about 50 background tasks on this CPU, which is very like, what is it doing with 50 processes on this thing? There is no preemption, it's all like cooperative stuff, and it's very interruptive, and like it gets most of the communication with the hardware via interrupts. In this firmware, it's not shipped with debug symbol, unfortunately, unlike some other parts of the Wii U that people talked about on day one, but it still contains file names, because like, they have these asset statements just about everywhere in the code base, and like, the asset statements, if it fails, it just shows up the file name in the source code. So from there, we can actually get like a very simple idea of what's like how the code is organized. So there are four main types of modules: drivers, which are basically the modules handling communication with hardware; services, which are the network handling part, like the UDP servers and UDP clients; managers, which are basically what the services talk to do stuff, and they contain like states and communicate with drivers and send data to services and stuff like that. And also applications just for all the code that actually like needs to run on the gamepad and display stuff on the gamepad and do stuff with controls and stuff like that. For example, like the TV remote app is an application. Another thing that really surprised us is that actually Nintendo in this firmware is using a lot of different types of inter-task communication stuff, sometimes completely redundant, and sometimes which don't make any sense. So if you have the usual data queues and barriers and semaphores and mutexes, they also have this system to register events which are called cross-process. And we actually found a case of using a memory pool with only one block registered to like do inter-task synchronization. So basically, this memory pool is like, it contains only one block of memory. So if a process takes a block of memory and another process tries to take another block, it will just wait until there is a block that is returned to the pool. So they actually use that to like do basically a mutex, which I still don't understand what they were doing. It's like probably like just an intern writing some code or something. But yeah, that's like what they're doing. So the other part of the CPUs of the gamepad is the UIC, the STM8 CPU, which is used to handle inputs. Fortunately, there isn't an official STM8 IDE plugin, but Megazik actually wrote one. It's really nice, it works well. And this CPU, as I said, communicates with the ARM9 code via SPI. and it's connected to all the devices. It has like an interesting point. All the settings for the gamepad are stored in its EEPROM. So if the main CPU actually wants to read some settings, it has to send a command to the UIC to read stuff from the UIC EEPROM, and then the UIC just sends it back of a SPI and just provides it to it. And they also don't provide high-level stuff to access these settings, so the UIC actually just sends back the whole blob of settings, which is 8 kilobytes or something, and the gamepad just parses it all every time. So video streaming, I'm going to let Geoffroy talk about that.
All right, so as you heard, we didn't have video streaming to the device actually working until pretty recently. And this was because, for unknown reasons at the time, but in order to figure out, we tried to look at the packets that were being sent on the stream and compare it to existing protocols, and we didn't find anything that looked really similar. So we just went to Hexrays and parsing the stuff ourselves to figure out what it is. And we assumed it carries H.264, partly because the DRH has some strings for debugging that suggests that, and we tried to prove that it was actually true, even though we couldn't decode it as H.264. So after reverse engineering the firmware on both sides of the DRH and the DRC, we were able to find out the meaning of the entire header of the vStream format. So the main important parts are the frame begin, end, and chunk end flags, and the timestamp played an important part. So just from staring at data that was going over Wi-Fi, we figured out the bits in the header and how they corresponded to frames beginning, ending, and chunks, which are kind of like H.264 slices ending within a frame being transmitted. And you can also see that the timestamp is being incremented at, well, it's probably hard to see here, but it's being incremented at a normal rate, which matches the 59.94 hertz, which is advertised. So we figured out the entire header and what it meant, but it still didn't help us decode the data that was being transferred in the payload. So instead of continuing to look at how the gamepad was receiving video from the Wii U, we looked at how the Wii U was decoding video it was receiving from the camera on the gamepad. And this turned out to actually be pretty interesting because it's not decoded on the DRH, even though the DRH has the hardware capability to do that. It's passed all the way up the stack through IOSU on the Starbuck onto the PowerPC, and then it's given to the GPU to decode. And the DRH plays a part in this by parsing the vStream format and converting it to UVC. And as part of that process, it prefixes headers on the reassembled data frames, and the headers turn out to actually match H.264 NAL encapsulation headers. So it provides the decoder parameters which are required to parse the compressed bit stream that follows. And in order to determine the actual settings that were being used, we had to reverse the UVD library on the PowerPC and determine the meaning of all the flags that would be used to decompress the bit stream. And this was actually a lot easier than I hoped after I'd reached this point, because they have this huge block of print statements for debugging, which lists the entire structure of the decoding. And as a bonus, it maps nearly one-to-one to AMD's Open Video Decode library, which you can find on GitHub. So certain bit fields were really easy to reverse from this. So this actually allowed us to decode the video stream that was in the payload. And as a side note, we noticed that the video stream didn't have any NAL encapsulation, which are basically just little markers on the beginning of frames to determine where the data starts, and it also escapes certain bytes within the stream so that you don't accidentally begin a frame when you don't mean to. So we could actually play a video here.
Just click inside.
So this is a video of the gamepad to Wii U connection being sniffed while it was running the Me avatar creation app. And after capturing it on the PC, we could strip the VSTRM format into normal H.264, apply the correct decoding stuff, and it worked correctly. So that was pretty awesome. And actually, we did that because we were hoping if we could change the resolution parameters on the stream, then it would also work for the gamepad video, and it did end up working to decode that as well. So now we can decode the videos, and because we have those parameters for the decoder, they're the same for the encoder. And we made an app that streams video to the gamepad, but it wouldn't work. We could get like maybe 3/4 of a frame displayed on the gamepad at most, and it would just freeze after that. So in order to debug this, we had to actually change code on the flash of the DRC in order to add debugging back to the host PC over UDP. So we reused some of the microitron code to open a UDP port and just write to it. So it was actually pretty easy to implement, and it allowed us to get all the assert statements that were in the code and dump things like the timing registers and other MMIO things that looked interesting. And after doing this, we found that the problem was related to the VSTRM timestamp in the header not matching the timestamp which the DRC was reading from some internal register. And this confused us for a while because the DRC actually has, well, DRC and DRH have about 5 timing registers which all appear to map to the same clock value. And the one that was being read for the VSTRM parsing is not written to ever, so we assumed it was just being started from 0 at boot or something.
Okay. So yeah, after some time, like we spent this, like we were stuck on this problem for a while because we just had this clock which was incrementing, and we couldn't figure out when it was initialized and how it was actually initialized. And then one day, like randomly, we noticed, hey, I just rebooted the device, and the value in the video timing register, like, is still incrementing at the same rate, and like it has a value that is consistent. Like if you interpolate the end time with the new start time, like it's basically incrementing at the correct rate, even when the gamepad is powered off. And actually, even when the gamepad was like, when the gamepad had no power with like battery removed, and we're like, what? Like, what's this clock doing? Like, how can it actually keep incrementing like when the battery is removed? It's like, it doesn't make any sense. And we're stuck on that for like a few days, and we realized, hey, actually, when you just disconnect the access point for the computer, like the timestamp just goes back to 0. And so it turns out that there is a weird Wi-Fi feature that nobody actually uses. That's called timing synchronization function, TSF. And what happens is that when you send an access point beacon, like your access point usually like sends beacons to say, hey, I'm an access point. You can connect to me. That's what you see when you scan for Wi-Fi networks on the net. So these access point beacons actually contain a timestamp, which is 64 bits in microseconds. And this is meant to be for stations, like for clients to synchronize the clock on basically the same value. And it turns out that this is actually what's being used for this video and audio synchronization. So we actually didn't even know about this feature before like finding out how it was updated, how it was updating the timestamp for video and audio. But yeah, it would be too simple if we could just use this timestamp value and for our video stream. So on Linux, there is actually no way to get the TSF value from userland. It's only available if you are like connected in Wi-Fi ad hoc mode or something, and then only on like in the dbgfs file system. But it turns out that most of the drivers still provide a way, like a standard way to read the TSF, and so we can just export it as a /sys file and give access to it to userland. But yeah, it turns out that then you hit other issues. So on wiring devices, we actually figured out that the TSF actually drifts slowly. Like after 1 second is passed, the TSF actually incremented the 1 second plus 10 microseconds. So the clock in the wiring devices actually go a bit faster than the real time. And it's actually even worse on Atheros devices, because it's not only 1 second, like 10 microseconds, it's actually 1 whole millisecond that it's going way too fast. And the timing window on the gamepad is actually only 1 millisecond. So it means that after 1 second, our clock has completely drifted away from the normal values, and we can't actually send it frames anymore because the timestamp just doesn't match anymore. And yeah, I mean, on Intel devices, it just don't provide anything for TSF. Probably because nobody uses it anyway, so it just returns -1 every time. I'm not even sure if there is a way to get it from the hardware. So this is one of the major problems we have with Intel devices at the moment and with Atheros devices. We couldn't actually find any explanation of why this is going on. When we actually asked to Atheros driver developers and ISCs, they told us, oh, it's not a bug, it's supposed to be like that. Which doesn't make any sense. I mean, it's a timestamp which is counted in microseconds, and it doesn't count microseconds. I mean, it's just a bug, but it probably don't want to admit it or have no way to fix it. So with that, actually, we were able to start sending some video data and get it properly decoded to the gamepad, because that was actually the only thing really blocking us. And we figured that out about 2 months ago, basically. But even when we're using the encoding parameters we got from the decoding stuff, we still have a lot of video corruption happening, and actually even crashes in some, because we still had our debugging code, and the debugging code showed us when the decoder actually failed to decode a frame. And when the decoder fails to decode a frame 2 times in a row, the gamepad just completely locks up and crashes. So we have to manually reboot it. And yeah, when using proper encoding parameters, it's still it happened. And so we just couldn't figure out what happened, and we found actually the feature that was causing this issue, and just disabled it, so now it's not crashing anymore, but there are still a lot of video decoding issues that you'll probably see in the demo. So yes, this is actually a screenshot for almost the first time we got video working on the gamepad. As you can see, we have a small grid. It's because we wanted to be able to debug the value of each H264 macro block, so 16 by 16 pixel, and that way we can actually see where precisely it's failing and why it's failing by just checking the stream with another decoder. So what's the current state of the project of today? We actually now developed a small C++11 library to be able for every developer to use the gamepad in PC applications. Currently it only works on Linux, mostly because on Windows we're just starting to figure out how to make the Wi-Fi access point and stuff like that, because it requires patching the drivers and patching the Windows Wi-Fi stack, which is closed source. But it works on Linux, and it should work on Windows at some point. It comes with nice demos and documentation about the API, but also about the hardware and network protocols, and how to use our reverse engineering scripts. One big caveat of it is that it doesn't handle all the pairing stuff and all the network stuff. It's completely separate. It assumes that the network is already working, that you're connected, you have the right IP address and stuff like that. So it's basically nothing actually. We haven't released anything to handle that yet. So if you have any patches and stuff like that, it's welcome. I think you should be able to access the libdrc.org website soon. It has all the documentation and stuff like that with the library. So yeah, disclaimer, it's an alpha version. It's extremely buggy. It's not meant for end users. Even getting the network right isn't easy, and it's probably going to take a lot of time if you don't know about Wi-Fi and stuff like that. But it's still a good prototype, and we're hoping that we can actually make it a very useful thing, and that some people will actually help us contribute to make it user-friendly and easy to use. So now, just some simple example code. This is how the API looks like. You just create a streamer object, you start it, and you can push video frames, audio samples, pour input to get the input data, and we have a nice feature which is enable system input feeder, which will just basically use the uInput API, which is part of Linux, to send all the controls from the gamepad directly back to Linux, and then Linux would translate that to emulate a real joystick plugged into the computer. So we can actually do in userland emulate a proper gamepad. So you don't have to modify anything in your application. If it already can use a normal joystick or a normal gamepad, it should just work automatically if you add this line of code, which is nice. Also in this release, just a few minor stuff, all the required patches for several projects. So X264 because we had to disable encoding features and stuff like that. Host AP for all the Wi-Fi modifications. Mac 802.11, which is the Linux drivers that handles Wi-Fi, basically. We released also some helper script for firmware with reverse engineering. If anyone is interested in that and has dumped his Wii U Gamepad firmware. We also have a very simple WPA2 passive sniffer, which will intercept communication between your Wii U and your Gamepad, and we'll try to show the video stream as it goes live. Unfortunately, because of how the video stream format works, it doesn't handle packet loss well, and you often have packet loss on Wi-Fi, especially when you send a few megabits per second of data. So it's just a toy, basically. It's not really usable for anything, but I just wanted to try it. And we have Wireshark plugins and Wireshark patches to be able to view the data. So now it's time for a demo, if it actually works. Because you know about live demos never work, but it's also live demo using Wi-Fi in in a building where 4,000 people are also using Wi-Fi. So let's see if it works. So just need to start the program. Okay. So now let's just run the gamepad. If it works, it should actually show our demo program. Yep, so this is just a simple demo, which allows us to basically do touchscreen and do stuff. I don't write well when I'm just holding stuff, but yeah, it's touchscreen drawing stuff, very easy. And we have a more fun demo than that. Let me just start it. So let's just restart the gamepad. This is one of the bugs, it should be automatically taking the new video stream, but it doesn't. Will it work? Yep. So does anyone recognize this game? So yeah, this is actually running on the Dolphin emulator on my PC. So this is emulating a GameCube on my PC and sending the video data to the gamepad. And as you can see, the latency is very good. Sometimes it just crashes, but it's not really that much of a problem. You can just restart it. Yeah, I said it's an alpha. I'm actually being beaten to death in the meantime. But yeah, the latency is very good. There are a few video artifacts still. But it's still mainly working, which is very nice. We really didn't expect such a good video latency and stuff like that, but it turns out it's just okay. So yeah, this was a demo. Thank you. So if we can just go back to the slides, maybe. Just have, I think, one last slide. Oh, yeah, this is just another screenshot that I had as a fallback. This is Final Fantasy VII on the PS1 emulator rendering in the Wii U Gamepad. But, yeah. So this is just like basically our to-do list of stuff that might be interesting to do. So obviously, like user-friendly tools already ported. I already talked about that. Windows and OS export. But also one thing that would be nice is Android port. Not to be able to stream video from an Android device to a gamepad, but the other way around. Like use the Android device and connect it to a Wii U and use it like as a custom gamepad. That's not like official Nintendo stuff. So I have with me an NVIDIA Shield. I don't know if any one of you knows NVIDIA Shield. It's basically an Android-based game console which has a touch screen and physical buttons and stuff like that. It's based on Android. So one of my current projects is to try to connect that to a Wii U and use it as a gamepad. One thing that would also be possible. Thank you. One thing that would also be possible actually is the PlayStation 4 and the PS Vita can do stuff like stream games to a PlayStation 4 to a PS Vita or even over the internet. And we actually think that this might be possible between a Wii U and a Wii U Gamepad using some kind of proxy system. We haven't actually tested that, but we don't see anything that would make it impossible. So if anyone just wants to try it, this would be actually a very cool feature for the Wii U. Fixing video encoding, obviously, I don't know if you've seen in the demo, but there's still a lot of, especially if you just look really at the screen instead of a camera looking at the screen, it's really obvious that there are a lot of video artifacts. Yeah, I mean, this is just going to be fixed by working with x64 people and trying to figure out what's not supported by the decoder and what we're doing wrong and stuff like that. Just a few other stuff, yeah. If you've got a data sheet for the DRC system on chip, we're obviously interested because we still basically all this hardware is custom and we have no idea how it works internally. We haven't found anything similar to the H.264 codec that they use, at least by looking at register mapping and feature sets and stuff like that. So I wonder if it's actually really custom or if it's just something that we haven't found. The firmware can actually be upgraded over the network, which is interesting because that means you can, if you have a device that can connect to the gamepad, you can actually do modifications to gamepad code, and it's not signed or anything. So you can just do whatever you want on it. So I have a project to just try to add a simple RPC stuff in this gamepad to be able to read and write memory and change some code and be able to experiment easily, and then maybe work on firmware replacement and stuff like that, because it's a device running ARM code. There is no reason why you shouldn't be able to run your own code on it. Anyway, if you have any idea about cool extension port devices to put on this gamepad, just try it out. It's just like an I2C port exported in the on the port at the bottom, so it's easy. So yes, that's all I'll talk. Thank you very much for attending, and if you have any questions, I think we'll be taking questions.
Yeah, we will be taking questions. If you have questions, just line up behind the microphones there in the alleys. So we have a question here on the far left.
Yeah, hi. How much of a chance does Nintendo have at blocking this stuff?
Oh, they probably could. The thing is, the flash not being encrypted on the devices, I think it's not something that you can change. So even if they start actually fixing stuff, we can still reverse engineer all the communications and do it again. They also don't have much of a point to fix that because it's not like it allows people to pirate games or anything like that. So we're not actually sure what Nintendo's reaction is going to be. We hope that they just let it go and let people use the gamepad for whatever they want. But if they start to fix stuff, obviously we'll try to adapt and fix our stuff as well.
I'm specifically worried that if you do something to the firmware, it will stop working after a Wii U update. So that would be kind of sad.
It's actually very unlikely that they can detect firmware modifications because there is no signature or anything like that. They would have to hash the firmware or something like that, and you can fake the reply. So
do we have another question maybe from the internet? Signal Angel?
Yes. Mindstorm is asking what CPU there is in the gamepad, especially the clock frequency.
What do you mean? Like what CPU? Because there are 3 CPUs basically, one ARM9, one Cortex-M3, and one STM8. But I don't know what the exact question is. Maybe I didn't understand it.
Sorry?
Yeah, but yeah, we don't know like a lot of details about all these CPUs because it's all custom hardware basically. Like the ARM core is a standard ARM core, but the system on chip is completely custom, so we don't have a lot of documentation about that. So stuff like CPU frequency and stuff like that, we have no idea yet.
Yeah, okay. Signal Angel, feel free if you have another question.
That's also far.
Okay, well, so, thank you.